Okay, good afternoon, everyone. So how we can use nitisinone to not to cure malaria or prevent malaria, but to kill mosquitoes. And by killing mosquitoes, we suppress transmission in endemic areas. And that's the concept. And just by serendipity, we were 2 blocks apart at the time. I was working in England from Ranga's unit. We didn't know he was working with patients. We started working with nitisinone because we thought that would be a good way to stop transmission. I will explain why we think this. So that slide, just to put things into context, malaria kills around 700,000 people, mainly in sub-Saharan Africa. 80% of them are children under 5. Okay, so there's no brainer, no more justification to this. Obviously, we got stalled into controlling malaria because of insecticide resistant, drug resistant parasite development. But then now, with the budget cuts that the new US government has implemented by eliminating, for example, USAID, this is going to be a rebound on malaria. It's going to be really tragic. And it's going to be quicker probably than HIV and TB because we can control mosquito population, basically. So why we got interested in this? So as I said, I'm interested in transmission. I study parasites and vectors, and transmission has to do with the process of blood feeding. So they have to take blood, mosquitoes, in order to reproduce. Okay, so this is essential for the life of mosquitoes. So this is, and this is not only mosquito, also you get other vectors responsible for all the diseases around the world. But when you block it, either pharmacologically or genetically, it tends to be lethal. That was discovered by a former postdoc in my lab, Marco Stergo, who then joined my lab and started working with different vectors, tsetse flies at the time, and then the work in mosquitoes. So I'm just going to focus basically on our work in Anopheles gambiae, which is one of the main vectors in Africa. And we have taken several routes into how nitisinone could be used, and that's thanks to the structure of nitisinone. So it's a molecule that it tends to be lipophilic, so it's got several properties. So obviously there have been a lot of work, and we know a lot about how the drug is metabolized in humans because of all the studies done by Ranga and previous investigators working on thalassemia type 1. And that's what I'm going to concentrate on in my talk. But we also been looking with Gates Foundation, looking into treating cows. So looking into determining the PK and PD profile of the drug in cows. And why? Because there is a lot of those vectors that feed on cows. So then basically you're killing several birds with one stone. If you treat cows as a bait, then you also reduce transmission, not only of malaria, but other vectors. So the compound also works, what we call this sugar bait. This is basically a bag of sugar. Mosquitoes need nectar to survive. So if the nectar is spiked with something that will kill them, then you get another route of elimination. And because the molecule is hydrophobic, it's also permeable through the cuticle, the mosquito cuticle. So as a contact insecticide also works. Now, the key with nitisinone or the inhibition of the tyrosine pathway for reasons that we don't know is that it's activated by blood meal. So that means that it's a female mosquito. Females are the only one taking blood meal, the only one that are vectors. If the female has no blood fed, nothing happens if it becomes in contact with nitisinone. Only when it takes a blood meal, then the killing mechanism in the presence of nitisinone kicks in. And that makes the strategy ecologically friendly because obligatory pollinators, like for example bees, they don't get killed by nitisinone. So that makes a huge difference with neurotoxic insecticides that kill mosquitoes but wipe out anything that you can imagine. Okay. So what happens is, so we established this collaboration with Ranga, and that's this paper that came out a few weeks ago that brought a lot of attention by the media, including National Geographic wrote a nice piece about the significance of how we can use this strategy to control malaria and other bacterial diseases. So that was done by a senior postdoc, now also faculty in Notre Dame, and a former PhD student in my lab, and my pharmacological guru gave, as you see, who has been participating in all these trials in the field. So this is just to basically show that the drug, if you do in the lab, you do what we call artificial membrane feeding for female mosquitoes, then depending on the concentration, they tend to survive or they get killed in a matter of hours. Those are some of the phenotypic changes. Basically, when in the presence of the drug, you can see that the blood is digested compared to mosquitoes that have not been treated. So if we wanted to go in that route, the concept of a poisoning mosquito with our blood is not new. Ivermectin does the same thing. It's a different mechanism. Ivermectin inhibits an ion channel, but we wanted to compare how it performs with ivermectin. And when we do the molecular modeling, looking into several weeks of performance with a treatment protocol, for example, for tyrosinemia individuals, we can see that it performs, nitisinone performs much better than ivermectin over time. Those are the concentrations that we calculated that would be mosquitocidal over time. And then what we did is the real experiment in the lab, feeding mosquitoes with the different concentration, calculated the different weeks. And we can see everything above the dotted line that represents what we call the hazard ratio, which is just basically mortality. And then you can see nitisinone performs much better than ivermectin. Okay, and then this is the model into what will happen in a malaria endemic setting in Africa. Dotted line is no intervention, and then the colors means the different treatment regimes over different months, and you can see that theoretically nitisinone will perform much better into reducing the incidence of malaria. But one thing is to mix blood with the drug and say we kill mosquitoes. Another thing is that would the drug, once it's metabolized in humans, will kill mosquitoes, still mosquitocidal. And that's when, by serendipity, we found out that Ranga was conducting these trials. So we were extremely lucky and happy to know this. He himself was extremely also enthusiastic. Actually, Ranga comes from Asia. He had malaria when he was a child. He was extremely excited about this. So we joined forces, we applied for the ethical license, and we got access to blood from our captonuria patients that have been treated with nitisinone. So we know how the drug is metabolized. And then when we fed mosquitoes with those drugs, we can calculate how much of this nitisinone stays over time, how much is mosquitocidal, and how much coverage over time we can model in an endemic area. And that's what we did. So these patients, this is a cohort that we haven't published. So after 2 days, so those are the levels of homogeneic acid, which is what accumulates during this disease. With nitisinone, then what happens is that tyrosine concentration increases, but homogeneic acid 2 days after goes to really basal levels. So this is just a snapshot of some of the patients. All of them are captonuria patients. 1 to 3 have been on nitisinone 2 mg per day, regardless of the weight. Patient 4 has never seen nitisinone, so you can see there is no mosquito mortality. And here, between 1 and 3, we can really see that depending on the plasma concentration of nitisinone, you can see different mortality, but it basically works very well, either neat or diluted in several ways. And then this is just modeling into each one of the conditions where we can see the performance, the PK and PD. And when we increase a single dose of 10 mg only, not per day, just 10 mg, how much coverage we get in terms of the days, and we get almost basically a week. Why this is important? Because in those areas that are affected by malaria, those are really poor areas, logistically speaking, and in terms of cost, we need to have something that ideally will be a single dose, but we have at least a month coverage. And this is our next step into suggesting that this might be used as a complementary strategy to control malaria. So I'm just going to skip this one. And we have been calculating some of these as well. So we have got, for example, this line here that represents single dose of 250 mg, only single dose, and how much coverage we're going to get. In principle, so we get at least 2 weeks. We have to test this and probably increase the concentration of it. So I have a couple of slides to finish. So we have an interesting situation with nitisinone. So nitisinone is made as a herbicide, is a weed killer compound that was discontinued by Syngenta because it was too strong as a weed killer. However, it had an extraordinary half-life of 54 hours in blood, and then was repurposed in the 80s and the 90s to treat thalassemia first, and then thanks to the work by Ranga Captonuria and other disease that Ranga mentioned, there are clinical trials at the moment. Now, what happens if we manage to repurpose these for vector-borne diseases, for example? Well, this group of people here represent at least 2 billion, a quarter of the planet affected by these diseases. So if we manage to make this cost-effective, it has to be less than $1 per treatment. That will have an impact to this group because the current cost of the drug are really quite high. So that's will be actually an added benefit that we think will have not only impact in what we study, but also into these communities as well. And just to thank the funders and I mentioned some of the people that work, and we are very grateful for this collaboration that we wouldn't be possible to do what we did. Thank you.